In this episode, you'll find out exactly how close a real Manhattan skyscraper came to collapsing and why the engineer who found his own mistake chose to fix it instead of hoping nobody noticed. 1978. A structural engineer gets a phone call from a student asking an odd question about a building he designed. That question sends him back to his own calculations. What he finds means his skyscraper, a brand new, award-winning tower in Manhattan, could collapse in a strong enough storm the public was never told. Here's why and how it got fixed in secret before anyone found out how close they came. In the 1970s, a new skyscraper went up in New York that broke almost every rule of conventional design. It stood on 4 massive columns, not at the corners, where you'd expect, but at the center of each side. The whole tower was raised on stilts, 9 stories up, to leave room underneath for a church that refused to sell its land unless the new building respected its space. To make that work, the engineer designed a system of diagonal steel braces arranged in a chevron pattern to funnel the building's weight into those 4 off-center columns. Elegant, innovative, celebrated as one of the most interesting pieces of structural engineering in the city. It worked exactly as intended. Nobody had any reason to think twice about it until the phone call. A year after it opened, the engineer got a call from an undergraduate architecture student studying the building for a class project. The student had a question about wind. Specifically, what about wind hitting a corner diagonally? The engineer's first instinct probably doesn't matter much. Straight-on wind is historically the worst-case scenario. But the question nagged at him enough that he ran the numbers for quartering winds anyway, just to be thorough. What he found wasn't a small discrepancy. It was a discovery that kept him up for the rest of that year. Here's the part that matters, and it's simpler than it sounds. Push on a table straight on, and the force spreads out evenly across that whole side. Push on one corner instead, at an angle, and something different happens. The force doesn't spread out, it concentrates. A much bigger share of it travels through a much smaller part of the structure. That's exactly what quartering winds do to a building shaped like this one. Diagonal wind concentrates it heavily on specific joints. For most conventionally shaped buildings, the difference is small safely inside the margin of error. This building's chevron braces weren't conventional. Because of those chevron braces, quartering winds put roughly 40% more stress on certain joints. That's massive. And the original calculations never accounted for it because testing against diagonal wind wasn't standard practice. There was a second problem, and it made the first one worse. During construction, to save money, the contractor swapped welded joints for bolted ones. The engineer's original spec called for welds. Bolted joints can be just as strong when installed correctly. The extra 40% of stress, combined with joints not built to spec, meant the numbers no longer worked. A storm expected roughly once every 16 years in New York could cause a critical joint to fail. And because of how the chevron system was built, that one failure could cascade upward through the whole structure. In plain terms, a fairly ordinary storm could bring the building down. The engineer had a choice most people never face: stay quiet, hope the math was overly cautious, or tell the owners the truth. The tower needs emergency reinforcement, and hurricane season is approaching. He disclosed it to the owners, facing massive reputational and financial risk, funded an emergency repair, and decided to keep it out of the public eye, worried that news of a possibly unsafe Manhattan skyscraper could cause real panic. So the fix happened at night. Welding crews came in after offices emptied out and reinforced the vulnerable joints with steel plates, welded directly over the bolted connections, restoring the strength the original design called for. Tenants working there during the day had no idea that above their ceiling tiles, crews were racing to finish before the next major storm. At one point, as a hurricane approached the coast, officials quietly discussed evacuation contingency plans in case the storm hit before repairs wrapped. The storm changed course. The repairs finished. The building never came close to failing again. The story didn't go public for almost 20 years until a journalist uncovered it in the mid-1990s. By then, the engineer had already accepted his reputation might not survive the disclosure. He made a real mistake, with potentially fatal consequences. When he found it, he didn't hide it. He reported it, helped fund the fix through his own liability insurance, and put public safety over self-protection. This case gets taught in engineering ethics courses specifically because of that choice. The mistake, an overlooked wind scenario, plus an unapproved material swap is a familiar shape by now. A design detail, changed to save money or time, never sent back through the original math. Honest question for the comments. If you made a mistake this big at work, would you have come forward the way he did? No judgment either way. I'm genuinely curious. Our first 3 episodes show 3 failures, 3 different root causes, a bridge that collapsed because warnings were repeatedly ignored, a plane that fell because a shortcut quietly became standard, a skyscraper that almost fell because of one overlooked angle in the math, saved only because one engineer chose to fix his own mistake instead of hoping no one would notice. Different industries, same shape underneath. That pattern is going to come back more than once. If you want to see exactly how that pattern keeps repeating across totally different fields, subscribe. This whole channel is built around finding it. Like this video if the engineer saves the day ending got you, and drop a comment. What should the next case study be?